Good morning, friends. In the last period, we have studied about the Maxwell-Boltzmann energy distribution function for ideal gas, and that equation is nothing but what we have to derive in that equation. That is, we have to n of E into dE is equals to 2 pi n upon pi kt raised to 3 by 2 e raised to half into e raised to minus e upon kt into d. This is the Maxwell distribution energy function of an ideal gas, and that function law, ideal gas law, that is continue to derive the Maxwell speed distribution. By using from that equation, we have to derive the Maxwell speed distribution. Now, for the Maxwell speed distribution, very important condition we have to consider here. That is, one more point we have to write here. We know that the Maxwell MB energy distribution law of a function of ideal gas is given by equation number, say, that is 1. And after that, for the classical ideal gas, there is a no interaction between the molecules and each molecule is distinguishable. For classical ideal gas, there is no interaction between the molecules. There is no interaction between the molecules, and each is distinguishable. Each molecule is distinguishable. Each molecule is distinguishable from one another, and here all the energy of the molecule is completely kinetic energy. What is the kinetic energy we have? Kinetic energy of the particle is nothing but E is equals to half mv square. E is equals to half mv square is the kinetic energy. Therefore, differentiating, B is nothing but what we have to say, that is 1 by 2 into bracket. We have to say that twice m into v into what we have to say, that dv. 2 gets cancelled, so dE is nothing but mv into dv. Now substitute this value of, say, E and dE in equation number, say, 1. Put in equation 1 the number of molecules, molecule nv into dv, whose speed lies between v and dv, v and v plus dv. Put this value in equation 1. Then number of molecules nv into dv, whose speed lies between v and v plus dv, whose speed lies between v and v plus dv, is given by, therefore, n of v into dv is equals to, we have to write that here in terms of E and D. We have to write this is for energy distribution. Now we have to consider the speed distribution, and again we have to write that 2 pi upon 2 pi n divided by pi kt raised to 3 by 2 into E is nothing but what we have to say, that half of mv, half of m into v half of m v square raised to 1 by 2 into raised to 1 by 2 into e raised to is nothing but what we have to say that e raised to each value काय आली आपली minus mv square divided by 2 kt into dE is nothing but what mv into dV, right? Now what factors we have to cancel here, that is some parameters we have to consider here, n of v into dV, and similar parameters we have to cancel in. Then what you have to get that is rearrange the terms we have, and this is what we have to say that m into parameters are what we have to say v is this, and here we have v square. V square raised to half means we have to cancel this one, and finally we have to write that is 2 pi n as it is, 2 pi n as it is divided by pi kt raised to 3 by 2 as it is. Here we have to say that this m raised to what we have, that is this can be multiplied by 2 and divided by 2. What you have to get that this is nothing but say 1 by here multiply 2 and divide by 2 means we have 2 raised to power 1, and the 2 raised to power half, that is next to say 1 by 2 as it is, and here we have m, this m raised to half and this m raised to say 1, that is we have to say that m as it is into raised to what we have 3 by 2, v square cancel, that is it becomes v square, this v square is cancelled with this v, and v into v is nothing but v square, and this m is nothing but m, and m is nothing but 3 by 2, and finally this can be written as e raised to minus v square divided by 2 kt into dV. This is we have to 2 into 2 is nothing but what 4. Finally n of v into dV is equals to 2 into 2 nothing but 4 pi into n, 4 pi into n. Bracket मध्ये काय येईल इथं, here this can be becomes, this is m raised to, in numerator that is m, and denominator what we have to consider say 2 pi k t raised to 3 by 2. Am I right? M upon 2 pi m k t raised to 3 by 2 into v square into e raised to minus m v square divided by 2 k t into dV, and this is the final expression that is called as what we have, the Maxwell-Boltzmann speed distribution law. This is 4 pi n upon into bracket m upon 2 pi kt raised to 3 by 2 v square e raised to minus mv upon 2 kt into dV. This equation is known as Maxwell-Boltzmann Maxwell-Boltzmann law of distribution of speed, law of distribution of a speed. Now case number 1. first case, what we have to say that is, in the Maxwell-Boltzmann distribution, we have to consider that if V is equals to 0, then N of V is equals to 0. V is equals to 0, then this factor is N of V is equals to 0. If V is equals to 0, then N of V is equals to 0. Means no molecule has a 0 speed. कुठल्याही मॉलिक्यूलला 0 speed असणार आहे. No molecule has a 0 speed. It means no molecule has a 0 speed. Now case number 2. In the case number 2, what we have to say that is, for the small value of a speed, for small value of speed, what we have to consider, that is mv square upon 2 kt. For small value of speed, mv square upon 2 kt is very, very less than mv square upon 2 kt is a very, very less than 1, and e raised to minus mv square upon 2 kt is equal to 1. Therefore, what we have to say that this factor is nothing but 1, and the value of nv is directly proportional to, say, v square. Therefore, n of v is directly proportional to v square. This is the second case. Means what we have to say that this factor mv square upon 2 kt, mv square upon 2 kt is very, very less than 1. Means we have to say that e raised to, this factor is nothing nearly equal to, say, 1. This is 1. Then all these parameters we have to consider as, say, mv is directly proportional to, say, v square, and the value of nv increases parabolically with the increasing value of v, attain the maximum value of the particle of the speed v. Therefore, value increases parabolically. Value increases parabolically. Now case 3. In the case 3, what we have to say that for larger value of speed, for large value of speed, v, what we have to consider that mv square upon 2 kt, this factor is very, very greater than 1. mv square upon 2 kt is very, very greater than 1, and minus e raised to minus mv square upon 2 kt dominates over the v square, and e raised to minus mv square upon 2 kt dominates over v square. Dominates over v square, and hence nv is directly proportional to n of v is directly proportional to e raised to minus mv square upon 2 kt, and then nv decreases exponentially with increasing value of v. increasing value of V. This behavior as shown in the graph below. This behavior is as shown in the graph. This is the graphical representation of, say, N of E versus V. As we have to say that N of E goes on increasing with increasing V at a certain value. After that, V MP, and what we have to say that velocity is increased up to that particular point, and then it goes on decreasing exponentially with increasing speed. This is the condition. What we have to say that NV is directly proportional to e raised to minus v square upon 2 kt. This is the exponential nature we have to observe in the case number 30. If mv square upon 2 kt is very greater than 1, and this law is called as a Maxwell speed distribution law. That is n of e dv is equals to 4 pi into n m upon 2 pi kt raised to 3 by 2 into v square and into e raised to minus mv square upon 2 kt into dv. From this equation, we have to explain these three cases. First of all, we have to remember the equation of the Maxwell-Boltzmann energy distribution of a function of an ideal gas equation, that is n of e dv is equals to 2 pi n upon 2 pi kt raised to 3 by 2 e raised to half into e raised to minus e upon kt into d. All the classical ideal gas, there are no interaction between the molecules. Each molecules are distinguishable and all the energies are completely kinetic, so that energy is equals to half of m into v square. So we have to consider that is half mv square is the kinetic energy. Differentiating this energy, what we have to get that? We have to get that is d of E is equals to mv into d. Substitute this value in equation number, say, 1. That is, we have to say that equation 1, the number of molecules n of E into dv, whose speed lies between v and dv, that is, energy distribution law can be replaced in terms of the speed distribution. That is, n of E into dv is equals to 2 pi n upon pi kt raised to 3 by 2 into half of energy is nothing but what we have to say that kinetic particles having energy, classical energy is half of m into v square raised to 1 by 2 into e raised to e की वैल्यू डालेंगे mv square by 2 into, say, kt into d is nothing but what we have to say that this is the value of d, that is mv into dv. Taking rearrangement of the equation, what we have here, m raised to half, we have to multiply this by 2 and divide by 2. It gets that is, this is m raised to half and this is m raised to 1. 1 plus half is nothing but 3 by 2 and 2 is here only half. That's why we have to multiply by 2 and divide by 2. That is 2 raised to 1 and 2 raised to half. It is nothing but 2 raised to 3 by 2. That is 2 into 2 is nothing but here 4. And here v square, as it is, what we have to say that is v square. This half is cancelled with this half. There it remains only v. V into v, that is v square into mv square e raised to minus mv square upon 2 kt. This is the equation into, say, dv. And then 2 into 2 is nothing but 4 pi n. 4 pi n divided by pi kt. This is pi kt raised to 3 by 2 and this one is 2. This is also 3 by 2. 2 pi kt raised to 3 by 2 into v square into e raised to minus mv square upon 2 kt into dv. And this is called as, say, the Maxwell-Boltzmann law for the speed distribution, or distribution of speed. And from this we have to discuss the 3 number of cases. First case is what we have to say that if the speed is nothing but 0, then n of e is equals to 0. This means no molecule has a 0 speed. And if for small value of speed, we have to say that mv square upon 2 kt is very less than 1. Therefore, e raised to minus mv square upon 2 kt is nearly equal to what we have to say that 1. It gets that mv is directly proportional to, say, v square, the square graph. That's why it is a parabolic. And then if its speed should be larger value at that time, mv square upon 2 kt is very greater than 1. Then e raised to minus mv square upon 2 kt, this dominates the v square. So when this value of e raised to minus mv square upon 2 kt dominates the v square, the graph changes to what we have to say that nv is directly proportional to e raised to minus mv square upon 2 kt. Means nv decreases exponentially with increasing value of v, and the behavior of graph is as shown in the figure. The graphical explanation is what we have to say, that NV is initially goes on increasing up to the particular value, and its value should be the maximum, that is called as most probable value, and after that its value goes on decreasing with increasing NV, that is an exponential change in the graph. So we have to say that NV is directly proportional to e raised to minus mv square upon 2 kt. In this way, this chapter is today we have to finish, that is statistical statistical distribution, and after that we have to continue the new chapter in the next lecture. Thank you.